Good evening, everybody. I think I know most of you. I'm Isla Berman, the Director of Architecture. It's with great pleasure that I'm able to welcome Sheila Kennedy to CCA and introduce her as our lecturer this evening. Sheila Kennedy is a founding principal of Kennedy and Violich Architecture, KVA, an interdisciplinary design and research practice based in Boston that explores relationships among architecture, design technology, and expanding areas of materials research. In 2000, Sheila founded MADEX, the Materials Research Unit of KVA, and developed an expanded interdisciplinary branch of the firm to focus on the development and integration of new innovative materials and industrial design components for architecture and infrastructure, including smart textiles and sustainable digital and energy harvesting materials. KVA and MADEX's field of exploration have expanded the traditional domains of architectural research and design practice, as is evident in the range of awards that they've received and the many different conferences, publications, exhibitions that they've been involved in that have included venues such as Domus and ID, but also things like the GeoTimes, Science News, the Discovery Channel, the TED Conference, Business Week, and The Economist. In the tradition of truly remarkable interdisciplinary and materials research-based architectural design practices of the past century, such as that of people like Charles and Ray Eames, where future-thinking technological experimentation with plywood, metal, and plastics operated in concert with architectural design innovation, KVA MADEX have carried this tradition forward through their explorations of things like electroluminescent plywood, microbial fuel cell research, and semiconductor integration into building materials and smart fabrics. MADEX has also developed new technology applications for DuPont, Siemens, Ostrom, Herman Miller, Saint-Gobain, the North Face, and the U.S. Department of Energy. The MADEX Portable Light Project, a nonprofit global clean energy initiative for the developing world, has been recognized with a 2009 Congressional Award as well as a 2008 Tech Museum Award. In 2007, KVA won the Chicago Athenaeum's prestigious Good Design Award and the Grand Prize for Building Innovation from the U.S. Green Building Council. Sheila's firm has received also many additional honors, including the Matter X Award for the use of innovative materials in architecture, AIA Awards, Progressive Architecture Awards, an AIA National Library Building Award for Design Excellence, and also a Distinction Award from ID. Their work has been involved in numerous exhibitions, some of the most prominent are the Design and the Elastic Mind exhibition at MoMA in New York, the Second Skin and Open House exhibitions for the Vitra Museum in Germany and Norway, the Extreme Textiles and Design for the other 90% exhibitions at the Cooper Hewitt, and the International Architectural Biennale in Rotterdam. The firm's design work and research has also been published in numerous books and journals, something that you should definitely look at. In addition to being principal of KVA MADEX, if that wasn't enough, Sheila is also a professor of practice at MIT. And prior to joining the MIT faculty, she was the director of the post-professional graduate program at Harvard Graduate School of Design for 10 years. She has also held many distinguished professorships, including the Eliel Saarinen Professorship for Distinguished Practitioners in Architecture at the University of Michigan and the Friedman Visiting Professorship at the University of California, Berkeley. In 2008, Sheila Kennedy was selected as a Fast Company Master of Design, MAUD, awarded to insightful and original thinkers who are designing new ways of working, competing, and learning, leading the high-impact innovators and creators who are defining what design means today. Please join me in welcoming Sheila Kennedy.
Thank you for that very generous introduction. When she started going, Isla started going backwards in time, I thought, wow, how far back is she going to go? So it's really nice to be here with you, to see so many friends. You know that Frano and I are frequently in California, and in fact, 3 weeks ago we were at Capitola surfing with our kids, and two people came down with surfboards and self-identified as two architects from this school. So, yes, hi, Michael. Hi, Michael. True story. We didn't practice that. What I want to do is invite you to think about materials and their effects, and to share with you a kind of a trajectory that at this point, when we look at our work, the work that we're doing, Frau and I feel like we've made a journey, we've made a kind of a trajectory, and this is what I'd like to kind of share in compressed form in tonight's talk. And so this is a sort of a personal and a professional trajectory. From thinking about what materials do, what their effects are, to thinking about how in architecture we can talk about agency and act in architecture. And so what I'd like you to do is look at the kind of whiter part of this image pretty hard. You can, don't look at me, just look at that and stare at it. And then shut your eyes. And if you've looked at it long enough and then shut your eyes, you still see it. You still see the areas of white, but they begin to transform, they change color, they drift, and each person has their own kind of area of transformation. And this is called the persistence of vision, and it's also the kind of after effects. So in both of those senses, a persistence of vision is a kind of a transformation, and it also refers to the kind of tenacity, the kind of willpower that an architect needs to have to kind of affect cultural change, which I think is one of the most important things that architecture can achieve. So this is the space in which we work. It's really the space made in the triangle between digital materials, semiconductor materials, those materials that harvest energy from the sun and turn that into electricity, for example, or the other side of the same semiconductor coin, those materials that take a little bit of electricity, very little bit of electricity, and then make light, architecture, and infrastructure. So we're always somehow working on projects that intersect in that area. And people are always saying to me, wow, you're so lucky you get to work with these awesome new materials, that is so cool. But what people don't realize is a kind of a dilemma that's been articulated by Clayton Christensen at the Harvard Business School called the innovator's dilemma. And in a nutshell, the dilemma is that new materials are always underperforming those mainstream materials and technologies that they compete against. So as a kind of a theme throughout this talk, I'm going to try to show you how we take underperforming materials, or materials that are very small, whose outputs are very small, and how we are trying to kind of aggregate those physically, how we manipulate those to aggregate those, and then technically how we also can collate light and also power with a kind of firefly as a kind of an instance. The firefly is one of the few animals in nature that actually fall into synchrony. Entropy is actually less of a factor here. They fall into sync. The male fireflies synchronize their flashes because over a million years of evolving, they found that that's to their benefit. They can attract females, and so they don't have to go it alone. They flash together. It's a form of social communication. It's like dating if you're a firefly, and it's effective, and it makes a larger amount of light so that they can be seen and they can attract females. So how can we take underperforming materials that may have the potential to be very efficient, that have the potential perhaps to transform architecture or to transform how we think about materials, and how can we actually work with them in ways that are effective? So for example, we've been fascinated with the idea of materials that themselves can be hosts for light. And with the Give Back Curtain, we developed a way to take a kind of thirsty natural cotton to integrate semiconductors inside these clumps of fringe that have moved from a traditional border, we all recognize a fringe, into a kind of figural position in this cloth. And then to organize these. So you can see the kind of drawing here, semiconductors, conductive wires that we've woven through, and they culminate in a little microprocessor that we harvested from a toy that we got at Toys R Us. So this way of organizing the on-off capability of digital technology is very cheap. Go to Toys R Us, harvest the parts from toys, you'll have the beginnings of a great prototype. So we can kind of cut it, we can make a basket of light, and so forth. And so this little MPEG will show you a little bit about a new way really of delivering light within materials. It's more fluid, we can easily program this, and the change in color that you're seeing is the Stokes shift. The shift from absorbing light at one part of the spectrum and putting it out in another part of the spectrum. So I'm going to talk about the craft of light and different ways in which we take the component or the part and then we think about the whole and the multiplication of that. And I'm going to move back and forth between more traditional or passive forms of working to more active technologically embedded forms. This is a project that we did in Massachusetts, in the western part of Massachusetts, for a metal and woodworkers workshop, and it deals with a kind of condition of dappled light, the kind of holes that when you look up, for example, in a tree, you see these like daubs of light. And in fact, dapple comes from a Norse word which means pool or hole of water, a little tiny pool, a hole of water that's reflecting light. So this project announces itself in a very kind of modest way. It appears to be a little bit deceiving, like architecture generally should be. And so it appears to be a very horizontal, simple project. There is a barn here, there's a workshop here and a large canopy, and then at the middle there's a skylight that faces north and it's a circulation system. But immediately, when you consider the section, you see the surprise. This project was built upon an existing foundation, an existing basement, so that the horizontality from the outside is kind of replaced by really 3 stories of space on the inside. And along the interior wall, in collaboration with the metalworkers, we developed a way to take the quality of dappled light from the outside and kind of bring that in artificially and pixelate it around in a pattern. And you can see some of the effects of this. This is a collaborative project where we developed the system, and all of these kinds of bumps and pixels were developed. Below here is welding, up is and metalwork, upstairs is the other part. The kind of horizon that you can see here that wraps around, 3-story gantry crane that moves in and out through here, and the kind of vertical surprise of being in this space with a light reflecting on it. In the barn, we were able to get some kind of transparency and conditions of cracks in here. Now, thinking about actually taking light, dynamic light, sunlight, and moving now to actually moving light digitally. This is a new project that just was completed at the University of Pennsylvania. We've been doing a couple of projects there. It's the Motion Capture Labs. And here we were working in this building, which is the Moore Building of Engineering. This is Todd and Billy's new extension to it here. And our project is really at the juncture of these 2 buildings. And you can see that here. This is the start of Skrakanovich Hall, which is Todd and Billy's building. And this is the Moore Building. So we had a large, pretty challenging, technically challenging motion capture workshop to do, and then 2 public corridor systems here to renovate. And we were interested in using the motion capture technology where, of course, you put different targets, light shines on it, reflects back into a computer, and you can actually capture human motion. This is a view of the motion capture lab and the connecting space. It's actually not a rendering. Some people have said this is a rendering, but this is actually the real photo. This happens to be a mirror so that you can get a kind of an infinite sense here. And we did everything that we could to try to raise and curve up the ceiling, which is impacted because there's an existing stair that goes up. This is another view looking back at a very large interactive corridor that I'm going to focus on. I'm really just taking certain building components, walls in this case. I'll talk about floors and ceilings, and I'm going to highlight them in this talk. If you want more information about the entire building project, come and ask me afterwards or check it out on our website. We're uploading it. So this is a very long 50-foot corridor. There's a ramp. It connects with another important walk, and this is basically engineering's main crossroads. This is the ENIAC, the world's first computer, which UPenn owns. And so this is kind of a giant technology crossroads in the School of Architecture. We did the motion capture studio, which was really interesting, and we decided to use some motion capture in that corridor. So we started with just videoing And we videoed a number of different people walking, as you can see here. And then using the software processing, we inverted that so that we get a white figure of someone walking. And then using some standard off-the-shelf Philips LEDs, we developed a system for this where we have a set of LEDs here, and this is a number check that we did along this corridor. So the corridor is quite narrow. It's probably about 8 feet, and it's a busy corridor. And we collapsed into the space of kind of 1 inch these LEDs and developed the idea of the virtual companion, so that as you walk down the corridor, your image is filmed, and the minute that you leave the corridor, it's assigned randomly to someone else, so that you have a companion, which is a light shadow, a memory of someone else who's walked in that corridor within the last 24 hours. So, how do you take an idea like this out of the museum? How do you take this out of the realm of installation and really put it into architecture, and then do that for a university project where, you need to pay attention to every detail? So I'm just going to share with you a couple of the details because I think they're unconventional and kind of interesting. One is that these lights come on fixed strings of fixed lengths. You can see here that we're looking at different densities, a heavier density and a lighter density, so that we were able to kind of bring resolution as we walk up the corridor. The figures get more resolved. As you walk down, they get completely more pixelated until you run into an actual screen here where for 1 second you actually see an image, a fleeting image of the person who's been accompanying you down the hall. This is the system architecture, the sensor detail here that's set into the stone. This is all the systems architecture, in other words, all the different strings and so forth, also part of our working drawing set, also part really of the architecture of realizing this. So this is really kind of what it looks like. You're walking down. And then a woman who's got a companion. Okay. So this project is really about the kind of energy that comes when light is constrained and you have a condition of being ajar, or the kind of the door ajar, the window ajar, or kind of cracks of light. This is the Madden Dance Theater, and the topic of interest for us here was really the kind of space that was made by the dance floor. This is a project in Providence, Rhode Island. It's a gym and a dance theater, and there's a public entrance to this existing school here, so this is an important public pathway. North-facing element opens up, you can see here, to the kind of public playground of the school, and this is the dance theater. And this project is very much about a set of screens and a skin that wraps around this building and the floor that's contained within it. Those of you who've worked in offices or who are in practice know that we have a lot of constraints in the United States about handrails and the spacing of them, the overturning moment, and all this kind of stuff. So we said in this project, look, we're not even going to have a handrail. Let's just get rid of the handrail and instead have a dance bar, and we'll have an overprotected double mesh screen of expanded metal, and we'll harvest some sunlight with that in a kind of a moire effect. And you can see that happening here. You can see the very basic, simple materials that we're using. This is an acoustic material called Tectum. Normally it's white, but the back side of it is natural color, and literally one day a piece of this fell off someone's desk in our studio, and we looked at it on the floor and we said it looked better upside down than it did right side up. So we got permission from the Tectum factory to use it the wrong way around, and that left the ceiling free as a color field, which was quite important in this project. This is a main detail of the building section. This is the floor system that I'll be talking about here. And this is some of the kinds of reflectivity, the kind of continuity that you get of the dance floor virtually, and also of that screen virtually in the dance mirror. So we were interested in this project in what we call a still figure, which is the figure of this floor. If you look at it in the building's long section, it really doesn't look that exciting in the architectural drawing. It's like a still figure. It's just a line. But it's got a lot of depth, and it's got a lot of character, and it's important to the project. So we looked at having a low velocity floor here, which is not our invention. But in it you have about 2 inches or so of airspace, and air can move very, very slowly, and it can percolate up. This is an existing system. Slab, and we looked at laying down some EL film, which is the material that you have in your cell phone pager, and just putting a conventional sprung dance floor on top of that with this as the intervention. So always, whenever you're trying to intervene in construction, in architecture, you need to find a strategic place to do so, else your invention is not going to get realized. So we made a little tongue and groove thing here. I think we have another picture of it right here. Tongue and groove acrylic piece. It fits right into the existing joint. Normally, of course, the two pieces of maple would be joined on the dance floor. This is inserted. The air filters out through here so that you can just cut that floor more, get more joints, and then you have more air ports. Cut it less, and you have less air ports, so you can begin to, for example, concentrate coolness of air or disperse it randomly depending on how those joints are inserted in the project. So it's like dancing not only on air but also on light. This is the side then again that faces the public space and the kind of cladding that moves around this building. We're using a semi-reflective galvanized aluminum shingle with just one break in it here, so we get kind of a nice corner on this building. You can see that here and here. This is another project about cladding. This project is about lightness. How can we take a material that's really intrinsically heavy like stone and actually make it feel light and make it be filled with light and work with light? This is a large project that we're doing. It's the new law school at the University of Pennsylvania. And the challenge for us was to try to use marble in such a way that it collects light. And we started for a long time with this idea. We thought it would be enough. A couple weeks into our materials research, we realized it would not be enough, and this is the story of how that unfolded. Penn Law is, an eminent institution. It's in downtown Philadelphia, and this is the first law school. It is an important historic building, and it has a lot of marble, and it has a lot of depth. These windows are like 36 inches deep, and there's an incredibly detailed wood that's even deeper on the inside side, and this faces south. So we looked initially at a highly translucent type of stone called alabaster, and we were hoping to use that. But in Philadelphia, in the Northeast, that's a non-starter because of the water content with rain, snow, thawing, freezing, and so forth. So we went back to marble, which is a much more structural stone, more stable, and we developed a system for this south facade. This is the building, and I'm not going to go into it in great detail, except for to tell you that this is Sansom Street. Silverman Hall, the historic building that I just showed you, is here. And there is a complex of 4 buildings, including our new building that's part of the law school, and this is an important courtyard here. So our idea was to try to develop a system of shading, self-shading windows here, here, and then a kind of very large gesture, which you see in diagram here, that could relate to the entry of the law school. And of course, this is all calibrated, the size of the openings and so forth, to Silverman Hall. This is also a law school building, but it's a less important building called, architecturally important building called Tobman Hall. So you can see here the way that we're making the southern hood, and each of these blades of stone faces east and west. And so we're looking at a historic pattern of brick called the Flemish Bond, and we developed an algorithm using Rhino to manipulate the stretchers and headers of this brick, which allowed us to, and this is the script right here, which allows us to kind of study certain areas of roughage and certain areas of smoothness in the stone. And this is this is right off our printing press. I just wanted to share with you the way in which we're kind of taking a number of pieces of stone and cladding and then making them come more and more together until they actually form this fascia piece here. So this is a light study. I'm just going to go through this very quickly so that you can see that we're going to get light here from both the east and the west, partially because of this also, and partially because of the way that we're working the stone. So we're developing, as I said, a kind of a mural continuity where this reads as a wall, but as you come down, the stone actually opens up. It's all cladding. All of this is clad and cantilevered stone, and you can actually look through to the entry here. These are just screenshots. As I said, I just took this a couple days ago off of from the team, just to share with you. And then this then is the strategy There are individual pieces of structure, and you can see how this very simple kind of triangular cladding actually, and this piece is this way so that it meets up with the fascia, moves and rotates about itself and ends up in that position. And these are the different plan levels of that, if we take a plan at each of the stone claddings. This project is a project that we did for Herman Miller. We did this with Applied Minds, who are software engineers in LA. And I invite you to check it out and indeed to specify it if you are so inclined at www.convia.com. And Herman Miller approached us and said that would we be interested in a project about a programmable environment? And we said, of course. So they gave the value proposition for the design team, which was that billions of dollars are spent in the United States on drywall that's thrown away from renovation and new construction. About 28% of drywall in new construction is thrown away. And of course it ends up in landfills like this. So moving from a kind of an esoteric material like stone to a much more prosaic and ubiquitous material like drywall, this is a project about how we can eliminate that kind of waste in drywall. So the premise is to have a ceiling track here and a device, an infrared device, that allows you to select any motor. As you can see in the little video, you can select anything that has an electrical motor, be that a conventional light, a projector, a computer, and you can group it and associate it with a switch. And then when you're tired of that particular grouping, you can unassociate that. You can take those and turn those off. And then in a large open office area, this means that you can reconfigure your office without tearing up walls, without taking BX cable and electrical cable out, and without all of the kind of waste of time and money that tenant-owned spaces called churn. That's the premise of Convia. So our challenge was to come up with a 7,000 square foot proof of concept project in about 9 months. So you can see here the very first pass at the ceiling system with the tracks. This all had to meet code. This is the first solid-state lighting, energy-efficient integrated ceiling system that I'm aware of, the one that we designed for Herman Miller. And we're using cut-to-measure technology here from the garment industry to allow designers to specify parametrically the shape within certain bounds of any one of these panels here. And this particular panel in this demo can be tuned to any of the 1.1 million colors that can be perceived with LED light. So it's a different kind of system, ceiling system. We used a Boolean process where we can subtract certain forms, stack them up again so that you can have sprinkler flow through it. So this can work for new construction, this can work for renovation. It meets all BOCA building codes, it meets all electrical codes. I'm not going to bore you with all of that except for to say that it took a lot of work, and it works. So the paradigm is now honey. I shrunk the ceiling and it's in the mail. When I move from one office to the other, I can pack up the ceiling and ship it in FedEx boxes, like my friend Scott is showing. So to do this, we need a high flow system, and we need a really cheap material. Because if you are investing in a technology that's underperforming, like LEDs, and they're still expensive, so you need a host material that's dirt cheap. So we used recyclable PET in this DTI machine. It's called a roll-to-roll laser cutter. There's a flying jib here. And then you'll notice that there's very little material waste. This profile is matched in production with this profile here. So literally the only waste in this material is the burn area of the laser cutter, which is minimal. So we can go from a very conventional setup, this lecture hall setup, for example, at the GSD. This is at Harvard, where this is now used in media, and you can see the kind of ruffling effect. You don't see the ceiling, even though the water from a sprinkler in event of fire can pour right through that. And then students can set it up in any way that they want, for telepresencing like this, for a student lounge, and so forth. And I want to talk very briefly about a wall system that we made. This was also part of Convia, though it hasn't been commercialized yet. where we were able to take, really create a new kind of partition which has a DC energy in it, DC line. In other words, a direct current low voltage line. We developed a screen that could be done in a flat a water jet cut screen out of any kind of recyclable material, and a way of dressing that, as you saw here, and then connecting that with the Convia system, as you see here, the screen. What I like about this picture is this is kind of the wall now. The wall has become this. It's all of that flat stock material, that recycled sheet, and then these are the parts and pieces, and these are the effects of that. And this has been important to us in thinking about light inside spaces and also our soft house project. So I'm just going to move quickly through these. This is the New York City East River Ferry Terminal at 34th Street that we're working on, that's now under construction. You can see that is right here. It's actually just behind this building right here, sticking out. It's part of the whole East River system. We've designed 6 ferry landings. You can see them here. And they are a form family ranging from smaller elements to the larger 34th Street terminal. And the basic premise of this is that the ferries are going to be used by commuters who are going to go up and down the island according to Mayor Bloomberg's vision of trying to alleviate gridlock. But they'll also go to Staten Island, they'll go to LaGuardia and other places that are a little bit more distant. So we were kind of fortunate in this project because we had 2 constituencies. The folks who lived on the East River, and my partner Frano went to about 8 community board meetings. He worked with like 8 community board meetings, which is a lot in New York to get all the approvals on this. You have those folks who live here, and then you have the commuters. So as a hinge to bring them together, we decided to take the existing GPS system that was run by the Coast Guard. And this is a very robust system with satellites and everything. You don't usually get to have satellites in an architecture project. And so we said, you should, to the City of New York, you should make this more public. You should amortize your system, get more out of it. And so we're using it now for real-time passenger messages, for access to the web, cell phone communications, smart traffic reports, and so forth. So if you remember the partition that I just showed you, this is an idea where we're changing the scale and we're trying to put solid-state lighting within something that is not as thin as a single sheet of textile, something that is in fact so thick that you can actually walk along here. There's a maintenance catwalk. But we're working now on this project, and this is the first complete lens-like soft roof. This is a PTFE roof, which means it's a structural roof, and we actually moved to this to save on steel and to save money on this project. And we're working with Michael Stein at SPP, and he's developed a very, very thin way of triangulating all the forces here so that really this thing almost appears to float. So the section is the key. You don't usually get to build on water. So we were pretty interested in details like this, where the pier, 34th Street Pier, edges are revealed. We tried to make them as thin as possible. And we needed to add a walkway here for fire egress from the water side. And so we opened up a hole, light comes down, hits the water, and remember the water river level raises and falls. And then it bounces, the light bounces along the southern leading edge of this. This is a metal mesh material that's PTFE. It's made by Versailles. This is made by Saint-Gobain, so it's an entire system. And then we have these skylight wells that are carved out. All of the programming, waiting areas, ticketing, and so forth, bathrooms are in this very simple program bar. And we just have parapets so that we have all of the heating and cooling machinery just on top. So we had to keep that just as simple as possible. So this is a caustic net effect. This is a free effect. You may be familiar with it from seeing it maybe in a swimming pool or going underneath a bridge. And we were interested in this effect along this wall, which is a perforated aluminum wall, and in the metal mesh in the ceiling. We wanted to harness this effect and juxtapose it against the kind of digital real-time passenger messaging and so forth. So in this view, you see the caustic net effect, what that would be like, and the impact also of the kind of data lighting that comes from those very large skylight wells. So we made a number of really large mock-ups. This is the first project where there'll be energy-efficient solid-state lighting in a public project. Remember here, our appliance those of you who are in practice, our clients are such eminent entities such as the Department of Transportation, New York EDC, the Economic Development Corporation, and so forth. This is not a museum. This is not a private client. This is public work. So we're very pleased that we can do this. And this is a transformation at night where what read as a void now begins to read as this kind of ghostly figure, which actually becomes a kind of a signaling device when you are stepping back and seeing this from a distance. This is the working drawings. We are the prime architect. McLaren is the engineering architect and also is doing all the submarine and marine work. Ken Smith is our collaborating landscape architect, and Michael Stein, SVP, our engineers. So this is all of the geometry for making these. This is the catwalk. This is the detail here with the solid state lighting. This is all developed and under construction now, and the model gives you just a little bit of a sense of how we would like to see this piece hover above the perforated wall, which will be more translucent and less translucent according to the perforations. And a view of what that will look like when you're returning home in the late afternoon in your commute. I'd like to talk a little bit now about the Soft House project and how we look at light for energy. And the Soft House project was kind of the next evolution of the part that didn't really make it to commercialization in Convia, which is how can we rethink the kind of modern wall system with infrastructure trapped in between it? How can we make a more a simpler wall system, in this case using a grid shell, flat material, no studs, form it, design it parametrically, and take a very ordinary element, a curtain, and give it another role, the job to harvest energy and give back some light. So we're thinking about the curtain as having elements of flexible thin film solar material, which I'll show you in a minute. And these icons refer to all of the direct current things that you probably have in your house. Most of them, your radios, your PDAs, your computer, your digital camera. You might not have solid state lighting in your house yet. You might not have a Prius battery, but you will soon. So the idea is that this is a hybrid house. With an underperforming technology, you can't expect it to do everything. And so we readily acknowledge here in gray that there are going to be a number of AC appliances that are still going to be used. Your dishwasher, your laundry machine, these are high load elements. They're better suited to AC. And everything that you see there in yellow, a central curtain that goes up and down, and then a peripheral curtain that moves along from east to west on this house, could be, potentially could be, sites for photovoltaic materials. And we developed a way of getting different density according to location and budget. So the project started out, as I said, by saying let's rethink the kind of inherited modern practice in architecture of taking these junction boxes, of taking wires and encapsulating them in a stud wall. Why is it a good idea to take air in ducts, to take water in pipes, and to take electricity and pack that all together in the building services cavity wall? This is a practice of modernism. We have all accepted it. We all know about the MEC E set in architectural drawings, but it's really time now to question that practice and to see what other alternative modalities there might be. And Soft House and many other projects are really part of that thinking that I think needs to happen. So as I said, this is a grid shell. It's a grid shell because we have two convex forms that are coming together which allow us to have a skylight where needed. What's kind of interesting is that the plan becomes dynamic over time. The curtains move around the house and take different forms. They create privacy, different offices on different levels. They encapsulate the bedroom and so forth. Let me see what I can show you very quickly. A vision of the central curtain coming down. It's kind of like a giant flower that could make a space, actually. There she comes, our hostess, who comes out. And we had to really put vision to action. We had to really develop this. And this is a process that now has gotten very, very real, as I'm glad to show you in just a minute. We started really thinking about, again, a very affordable host with our friends at Svensson, an agricultural shade cloth company who we're working with. They have a Rochelle 3D knitting machine, and you can literally knit your house. You can knit your energy harvesting curtains, which is very cool. And then we can look at either a technology called CIGS or OPV. OPV is organic photovoltaics, which are made in a chemistry laboratory. CIGS is inorganic thin film photovoltaics. Both are not the most efficient, but they can do something. So what can they do, and what is the return on their investment? And this little diagram shows that. Okay, let's space this out quite a bit so we don't have a dense curtain here. Let's imagine 8 by 7. What's it good for? Here's one strip of this material. What capacity does it have? Well, it can charge that many cell phones. 3 strips, it can charge that many solid-state lighting diodes at 100 lumens, let's say. So that's, that, for example, would be 800 lumens. That's about as much light as you would get from one 60-watt light bulb. So one 60-watt light bulb, if you run a 60-watt light bulb turn your light bulb off for 6 hours every night, and instead use this solid-state lighting, and if electricity is at 19 cents a kilowatt hour, which is what it is today in the United States, then you can save about $80 a year with these 3 strips. So that tells you something about what the pricing of that needs to be. 24-inch long curtain, you can charge your Prius battery. So we started really thinking about this, and we looked at what can we take off of, this is residential loads. Of course, heating is a high one, but heating is very energy intensive, so that's not very appropriate for photovoltaics really of any stripe. So we said, well, look, let's take lighting and let's take electronics. We'll take a big portion of those because those are all DC. They can be solved DC to DC, no inverter, maximum efficiency. And then let's get these passive gains that normal curtains do anyway, insulation, shading, and so forth. And so it really adds up to about 50% in the United States, about 50% of the energy that would be consumed. We are working now with the government of Portugal on a very exciting project that's sponsored by the government of Portugal and the MIT Energy Initiative working on this. And the basic premise is to look at a historic district in Porto called the Casa Borghesa. This is a really interesting semi-abandoned central area. And this project is about the sustainable renovation and retrofit of these houses that are characterized by being very, very tall. Okay, floor to floor here is like 6 meters, sometimes 7 meters, which is really tall, 18 feet. Very narrow. This is actually a wide one. Some of them are like 2 windows wide, and a very long, thin footprint. So what we're doing is harvesting energy with canopies on the roof with the soft house technology, and using that for facade lighting on the one hand, which helps the city of Porto invest in this, and also helps homeowners by selling electricity to electric scooters, people in electric scooters, which helps take the historic area here in Porto and here in adjacent Gaia. This is where the port wine is made. It helps bring the mobility of the new Metro Porto system, which was designed by CISA. It helps expand that by having the last mile solution with electric motor scooters. So this is a typical section through a Casa Borghesa. This is the solar canopy. We are looking at how it might even roll down into the traditional central light well and central stairwell, which typifies this typology. This is a very, very interesting, very consistent typology. And we're working now with the government of Portugal in Porto to look at this for 20,000 households. So this image shows you a little bit about the variation and what that could look like. This is the last project I'm going to share with you. It's the Portable Light Project. This has a very simple but kind of breathtakingly ambitious objective, which is to provide clean energy and light in the developing world. And I urge you to go to our website, www.portablelight.org, and get more information about the project. We've been fortunate in the last couple of years to get a lot of good recognition, and I want to just give you the headlines first, and then I'll talk a little bit about really what this project is, because the headlines are kind of exciting. So what are some of the problems that we're working on? What is the scale of some of these problems? With Paso Pacifico, our partners, we're working in Nicaragua on this particular land bridge here. And this is really important. It's a skinny piece of land, but it's very important for migrating animals to travel from South America to North America. If we cut this off, then we are really running into a kind of a major, even worse, diversity problem. And there are a lot of sea animals that also pass by here. So with Paso Pacifico, this is a site where we're working. We're working here with a group of villagers who used to be turtle egg poachers. So there wasn't much work. They're very poor, and they used to make a living by killing turtles and sometimes grabbing their eggs and trying to sell them. These are the rangers now with Portable Light, Red Adopted Portable Lights. They are working with Paso Pacifico, who offers training so that they can take their local expertise, because they know where those eggs are, and they know those waters better than anyone else for ocean monitoring and for protecting the turtles. This is a much better livelihood for them and their kids. And then in the evening, the kids can use and the families can use the light from Portable Light. This is a kind of a weird image, but you can see two people with the red adopted lights here, because turtles are bothered by white light, and there are still poachers. And so the rangers, Paso Pacifico, self-identify with a red light. This project, Paso Pacifico's project, will be at the Clinton Initiative with Portable Light this September, and actually just in 2 weeks. Next partner, MGH, Massachusetts General Hospital, and Edendale Hospital. Sorry, my dot has moved. But imagine that this was right over here, right over KwaZulu-Natal. This is a big area and a really even bigger problem. The co-epidemic of what happens when people have HIV and they have multi-drug resistant tuberculosis, which is increasing in severity. So the hospitals are interested in looking at SMS texting technology, which can be used in a variety of different ways, where people in the developing world have cell phones. I think about 85% to 90% maybe even of everyone in South Africa, regardless of economic class, owns a simple cell phone. But less than 40% of all people in South Africa, which is an unevenly developed country, but it's a pretty wealthy African country, have access to electricity. So Portable Light is charging cell phones, and through texting messages, the doctors and nurses are trying to vastly increase the catchment area, because you can receive a text message for free in South Africa. And so people are reminded for their course of meds and so forth. And with Zinni Tabethele, who's a AIDS activist and an educator with the iTeach program at Edendale Hospital, we developed a kind of a traditional blanket, which is a hospital blanket with a Portable Light flexible solar panels, and also a pop-up textile lantern that's 100% textile. And that means that people who are very, very thin, because they've been coughing all the time, they get cold and they don't want to sit out in the sun, even though it's quite warm in South Africa. So with a blanket around them, they can sit out in the sun, they can stand that better, and they can charge a little bit of light. They literally are empowering themselves and their families during this very, very long process where they go through cycle after cycle of medication trying to get better from multi-drug resistant tuberculosis. And then in East Africa, here we're working on a project with San Francisco-based Timbuktu. And you can check this project out. It's just been blogged with AfroGadget. So if you look at the FLAP project, AfroGadget or Afro Musings or any one of those blogs, you'll see this story online. So I don't think I'm revealing anything. But basically in East Africa, a number of solar textile kits were given to people like this gentleman, a tailor, a local tailor, and they, and through Maker Faire Africa, are developing different ideas and different designs and forms that would be suitable for East Africa. And one of the ones which I think is kind of the most interesting is the Boda Boda rider. Here's a PL, a Portable Light Flex kit. In the Kinshasa area, there are like over 500,000 Boda Boda people who cross borders on the bike. They use the cell phone to get clients, and they take people the long distance between one African border and another African border. So hopefully this, and this is a proposal that was submitted recently, hopefully this will be an enterprise. So the main idea of the project is, can we replace this process of getting light with a new material? And we know that this process of burning is not very efficient. A candle, for example, gives you about 3 lumens of useful light, an LED anywhere from 50 to 100 lumens of light. But we have we have a liability here. We have an esoteric material. We have a thin film material that only has a kind of niche application through camping goods, let's say, and the military. So how can we take a needs-based problem, like the 2 billion people who don't have access to electricity, and accelerate this material's use in these contexts? This is the challenge, and I'm not saying that we've solved it. I'm saying that we're working on it. So our longest standing project has been with the Wixárika people, who are semi-nomadic people who live in the highlands of Sierra Madre in Mexico. We've developed textile lanterns, and this is an instance where you see a woman here who's going to turn off her light, and then she's going to get up and go out the door. And what's really shocking about this image of Alicia, it'll stop for a minute, you see she's going out and it's broad daylight outside. That's how dark her house is in daylight. Now you should really think about what that's like at night. So the lack of light, even though that seems like a really basic, simple, almost dumb thing in our context here in the United States, is very, very significant in terms of people who live in energy poverty. So with the Wixárika, and with the help of a number of different anthropologists and quite a large team of medical doctors, we looked at the possibility of connecting these bags, which are not accessories, they're actually heraldic family symbols, with the Portable Light Project. And so we were approached by a group of women, including Estela Hernandez, who's a master weaver. You can see Estela here. And she proposed that instead of us providing the solar textiles, she would make the host materials and she would create the textiles. And this was really the trigger that started every single of those other projects. The idea of co-creation, using local materials and designing the technology so it could be integrated using very, very simple traditional materials, weaving, sewing, and so forth. So here is Estela sewing in the solar panels and working with the first solar kits. And some of the amazing things that she produced, this is actually the LED here, she had it on a kind of a snake arm. We would make these little parabolic reflector kits on the computer and then flatten them out with developed surface, and then they could be a set pattern for people to work on. And the result then is a kit which includes a reflector, soft optics, our digital drive. We developed all the electronics for this, and either a 1 or a 2 watt system of solar panels. So I want to just conclude with the comment that when infrastructure changes, our culture changes. And we've been through this before. We've been through it at least 2 times. When we shifted from fire to gas, which is what this image is, and then when we switched from gas to electricity. When we switched from fire to gas, there was an enormous cultural shift. It affected the arts, it affected painting, it affected ideas of color. And people were very concerned with the kind of perceived homogeneity that this electric light was producing inside this. This is from the book Disenchanted Night by Wolfgang Schivelbusch. People wanted to put more shades and cloth over the filaments, even the very primitive filaments of electric light. So this caused a big cultural change. We have had about 2,000 years of thinking about how to deal with energy and light in its liquid form and in its solid fuel form since the early shell lamps of the city of Ur. If you think about it, we've had about 30 years of thinking about where solar technology should go. Ever since I'm dating it right back to 1978 when Jimmy Carter put the first solar panel on the White House. It was subsequently taken off again. But we don't really know for sure whether the roof is the best place, really what this infrastructure should look like at all. And I'd say that one of the greatest kind of acts of agency that we can think about as designers is to really imagine what this next generation of infrastructure will be and what its implications will be for the culture of architecture. Thank you.